Hi guys, welcome to this video. I'd like to present a code for frame or beam analysis using the stiffness method developed in Excel. The reason for doing this is that most students think this topic is difficult because sometimes the stiffness matrices look intimidating because of the size. But I assure you, if you understand what is going on, is something very simple. So why the new code? Of course, as you know, most commercial softwares are expensive, sometimes with complicated user interfaces. But when we talk about Excel, it is available to almost everyone with access to a computer. So you can literally make your own code, and the potential for this is limitless. So if we say a code, many people are scared. They think it's very difficult. So, but I assure you, it's simple, as you will see. So, what is stiffness? So, stiffness is the amount of force or moment or torque required to cause a unit displacement, rotation, or shear. So, for example, if you have a structure like this, oh yeah, so a structure like this is your structure. So if you assume the axis, if you assume an axis like this, so this is x, this is y. So if you say this is direction 1 prime, this is direction 2 prime, and this is direction 3 prime, the direction for the moment, and this is 5 prime, this is, sorry, just a moment, this is direction 4 prime, and this direction is 6 prime. Let me indicate this one a little bit better. This is the moment and the moment. So we know, so I need to say that the understanding of this assumes that one is familiar with determinate, statically determinate and statically indeterminate structures, and some basic understanding of mechanics of structures. So if in the axial direction, if you apply an axial load, then the displacement can be calculated as equals PL over EA but we are saying that the stiffness is when the force required to make the deflection unit. So if this is 1, then the force to get the force P would be then EA over L as the matrix. So in this direction, that E is positive. So You can see this value there. Of course, for equilibrium, if this is E A over L, for equilibrium this must be E A over L. So to get the stiffness matrix, you apply the force that causes a unit displacement in that direction and assume everything else is zero, hence the reason. So you can see positive AE over L, and at the fourth position negative AE over L, so both vertically and horizontally. So that's the reason. So to understand the other stiffness matrices, so in the second degree of freedom, using a similar example, so you apply a unit load here. To get a unit movement, there is 12 EI. Sorry, the diagram does not look very nice. So let me do a new one. So for the direction 5, sorry, direction 2, so if you have the same structure, if you got the same structure there, the same structure like this, like that, so if you apply a force in this direction, sorry, okay, the force in vertical direction, so a force that would cause a unit displacement is 12 EI is is 12 EI over L cubed. So as you can see, it's a little difficult to write, over L cubed, as you can see. So just like this, just like here. So when you apply this, then you also apply a moment that can cause a unit rotation, so 6EI over L squared. So from statics, if you're able to balance, you find this is the reaction and this is another reaction, and so you get this, the second column and second row. So just like that, so even when you talk about the third degree of freedom, you apply this moment and this other moment in the other direction, and then if you work out, these are the reactions, so and so on and so forth. So you get the third row and third column. But this can be better understood if you know what is called the slope deflection. If you don't know about it, I think is okay, but it can be better understood in the light of slope deflection method. So this is a little bit of introduction about it. So as you can see here, we are already talking about an axial force, represented in this case by EA over L. So first row and first column is talking about axial force. Second row, second column is talking about the shear force, and then third row and third column we are talking about the moments, and of course these ones the rest of this, the lower half of this is related to the above. There is related either to axial force or shear force or bending moment. So how about torsion? So torsion, in most structures, as torsion is assumed to be zero, but even if it exists, then there are ways to deal with it. For example, if there was torsion here, then we would maybe include it here. So we have another column for torsion there, another column for torsion there, and one row for torsion there, and another row for torsion there. So we would have, this would then transform from a 6 by 6 matrix. So the 6 by 6 matrix, then it would go, if you include torsion, would go to 8 by 8 matrix. And so the most general stiffness matrix is, for example, if you have a structure like this, and then can only be loaded in the following ways. One, we have an axial force, which is represented by N, shear force represented by V, moment represented by M, and torque represented by T. So those are 4 forces. And then if we have different nodes, so let's say this is node 1 and node 2, so the 4 forces on node 1 and another 4 forces on node 2. And we have 2 planes, so there's the vertical plane, the called plane 1, which is just, plane 1 is, we're just referring to this plane, so this is what we are referring to, plane 1. And plane 2, the plane perpendicular to the slide, so represented, shown as shown. So like I introduced before, the contents of this matrix, I hope you're not intimidated by the matrix. It looks large, but you already know what it contains. This is just this. That's the basic. So if you were to include torsion, then you have torsion, for one for torsion, another column for torsion there, a row for torsion there, and a row for torsion at the end, so that this 6 by 6 matrix would become 8 by 8 matrix. So if assume this structure were to be loaded in the 2 planes, then what would have is the 8 we are talking about. So this is the 4 forces in plane 1 and 4 forces in plane 2. Then the 4 forces in node, sorry, these are the 4 forces in node 1 plane 1, and then 4 forces node 1 plane 2, then 4 forces in node 2 plane 1, and the 4 forces in node 2 plane 2, the same as you go down. So at the end of the day, you have a 16 by 16 matrix. The reason for this is most people, when they see this, they get confused, and sometimes they see a very large matrix and sometimes they see a shortened form, so they are confused, they are not clear exactly what is happening. So this is a principle, this is how this usually is condensed. So, but the good news is that the loads that we are dealing with are predominantly gravity loads. So that means the load in plane 1 dominate most of the time, because the loads in plane 2 are transient. I'm not sure that's a good word for it, but or temporary loads like earthquake or wind or typhoon, etc. So, and we cannot design a structure assuming it will be loaded with transient loads through the entire lifetime, as it would not be economical and it wouldn't make sense. So for this, we design special we have special design considerations. For example, for earthquake, you can talk about seismic isolation, or shear walls to carry horizontal forces. So these are some of the mechanisms to deal with the transient forces. So in most cases, we assume the loadings in plane 2 do not exist, and so this is why we cancel out all the plane 2 loadings. So as you can see, the plane 2 loadings are all cancelled out. Plane 2 loadings are all cancelled out in both horizontal and both vertical sorry. So both horizontal both horizontal and vertical the matrices, we assume that the horizontal loads do not exist, and you can see how we reduce the 16 by 16 matrix to 8 by 8. So you should not forget that even though it was a 16 by 16 matrix, it only consists of the four things: the axial force EA over L, the shear force 12 EI over L cubed, and sometimes 6 EI over L squared, the moments and the torque. That's all. And then the node, whether it's node 1 plane 1, node 1 plane 2, or node 2 plane 1, or node 2 plane 2. So how do we evaluate the stiffness matrix? I think we already did the introduction. When I explained the source of this, which is 6 by 6, and this is the most typical one we use. I said if you wanted to include torsion, so this is one for torsion, you can see one for torsion, another layer for torsion here, a column rather, not layer, column for torsion there, and a row for torsion where, another row for torsion there, and row for torsion, and then this increases the matrix from 6 by 6 to 8 by 8. But again, if you don't want them, or if they don't exist, you just assume and then you remove, and then you remain by your 6 by 6 matrix as has been discussed before. So how about if you are interested in the 16 by 16 matrix at a glance, how would it look? So the good thing with the stiffness matrix is that it is symmetrical about the diagonal. So for example, we said this from here to here to here, we are talking about node 1 plane 1, and here to here is a different color. Here to here node 1 plane 2, and then there, and node 2 plane 1, and then node 2 plane 2, and the same order going downwards. So we have a 16 by 16 matrix, but the content are the four principal forces that I've already introduced before. And if let's check the previous. Oh, sorry, we can't go back, but even the previous matrix we discussed ahead is symmetrical. You can see if you check this matrix about the diagonal, it is symmetrical about the diagonal. So if you if you check this here and check, they're the same. So again, if you put the mirror here and check there and there, they're the same. Again, from here, if you put the mirror there, check this, they're the same. So this matrix is symmetrical about the diagonal. That is one beauty. But as long as that matrix has not been transformed, when it is transformed, it is different. So the governing equation is the reactions are like this. So this reaction N, V, M, and T equals the stiffness matrix times the displacement plus the fixed end moments, and fixed end moments are usually determined from standard tables like this. So it should be should not be very difficult to do. So from here we can say that so the reactions, let's call the reactions R, equals stiffness matrix K times the displacement matrix times the displacement matrix, difficult to write, times the displacement matrix plus the fixed end moments, so FEM. So if you, I think I can write here. So if you say the reaction matrix minus the the reaction matrix minus FEM matrix becomes the load matrix P. So here, so then we can say the load matrix equals the stiffness matrix times displacement matrix, and hence we come up with this equation. So to solve this is basically you take the inverse, you multiply the inverse of the stiffness matrix by both sides. So when you multiply that, when you multiply this stiffness matrix by the inverse, you get the identity matrix. You get the identity matrix. So if this becomes the identity matrix, this becomes the result of this is the identity matrix I. Then once this is the identity matrix I, then you're able to solve for U. So basically U equals the stiffness matrix, the inverse, times the load matrix. So that's all. And this is where Excel is going to help, because this matrix, be it 6 by 6, 12 by 12, Excel by using very simple code is able to solve, and then you're able to identify, you're able to solve the displacements. So we use some example to verify the code. We said that for computer programs, garbage in, garbage out. So to verify your data, you must use a real example and see whether the program is able to give you the required or expected results. So I'll go over this example first, and later I'll get into the Excel code. And the codes in Excel will be useful even in non-engineering applications, because the commands sometimes can be applied in other areas. So it's not only for engineering or civil engineering applications per se. So this can be useful in non-engineering environments also. So just consider, because of the different orientations, there is what you call local axis. So local axis for member number 1. So if you call this member 1, you call this member 1, this one member 1, and call this member number 2. So this is 1, and that's member number 2, as shown here. So the local axis is just considering the axis of the member without considering the other members. So just for example, the local axis for member 1 is just this. So just the local axis for member 1 is just the usual axis x and y. So, and then the local axis for the member 2 is just the direction, this and that, without independent of member 1. So those are the local axes. But the global axis is considering the general direction, considering both members 1 and 2. So global axis is shown as shown. And so for the member 1, so to get the stiffness matrix, you first need to determine the local stiffness, the stiffness matrix in the local axis. So what you do is just substitute the properties of EA and L according to this arrangement, and the beauty, like I've said, it has to be symmetrical. So if you check this, is it symmetrical this way and that way? Again here, if you check, is it symmetrical this way and that way? So just substitute the values EA and L, then you arrange it the matrix as shown. So this is the Excel solution. This is the Excel solution. This is the Excel solution, and this is the example from which I borrowed from. Incidentally, actually, in academics is a good thing to attribute authorship appropriately. This example I whipped from the internet, although I'm not able to exactly attribute authorship because it's not indicated, and nonetheless I think is a good example because the way they demonstrate the example, the example is good and easy to follow. So this is the Excel solution, and this is the solution from the example. And to calculate the fixed end moments, you just assume that you isolate the members. For example, member one, you isolate it and replace the supports by equivalent reactions. So if you isolate member one, that would be the vertical force, horizontal force, and of course there will be a moment there, and then there will be another vertical force there, horizontal force there, and of course a moment. And when you add the load, then you calculate the this is the stiffness in the horizontal. This is the non-transformed. This is the stiffness in the horizontal. So stiffness when the member is assumed horizontal is this. So times the transpose, the transpose of the transformation matrix times the stiffness matrix times the transformation matrix gives you the stiffness matrix in the required orientation. So this is the transpose. This is the transpose. I'm sure you know transpose is just this is the transformation matrix. So transpose is, for example, this becomes the column. So this becomes the column there. Alright, and this, the second row becomes the second column. That's all. So you rearrange like that and multiply with K. That becomes the stiffness in the correct orientation, considering the angle. So this is 56.31 and this is 76 because the roller support, I think as shown, was in an orientation of 20 degrees from the example. So 20 plus 56.31 is 76. And so for the second member, again we use the same stiffness matrix. So if we assume we have not transformed it into the orientation, so you just substitute here. Once you work out the orientation, the length I think is 3.6 and the E and the A 3.6 meters, 3.6 meters. E and A is given, E and I is given as before. So this is your stiffness matrix. You can see, so if you hold this here, check, is it symmetric? And indeed it is. So this is symmetric. But here you need to also pay attention, is only symmetric before it is transformed. After the matrix is transformed to a different orientation, the assumption of symmetry is no longer valid. So we can only check the symmetry here, and because you have not transformed it, it is symmetric. You can still see here, and so on and so forth. So it's still symmetric, but after transformation, the assumption of symmetry is no longer valid. Again, compare. So this is the expected value from the example, but this is the result from Excel code. I think close enough, or barely the same. Maybe there is slight variation because of the rounding off. The difference is the rounding off of the angles. And so when you multiply, so you get the stiffness in the correct orientation. So the transpose of transformation matrix times the stiffness in the horizontal direction times the transpose stiffness matrix, you get the K star, or the stiffness of the matrix in the required direction. So here, that's what you do. So this is the result of the multiplication. Incidentally, I think it's still symmetric, because if you hold this, if you check, I think it's still symmetric. Yeah. So, but anyway, sometimes depending on the angle, after transformation, the matrix may no longer be symmetrical. But in this case, it's still symmetrical. You can see if you check here, so it's still symmetrical. So this is good. Symmetrical. If you hold this here, yes, still symmetrical. So this is a key way to tell whether your result is good or not. So just know the stiffness matrix, the non-transformed one, and even in this case, the transformed one is still symmetric. The same, I think this one has a 10 power 3 outside, so should tally with the Excel solution, with our Excel solution. So this is highlighted because this is for member 2. This is for member 2, and this part is going to overlap with member 1. So it's highlighted because you have to add the two stiffness matrices in this position. So in this previous stiffness matrix, these have some value. This is why in the previous part we call them 4. We call them 4 underscore 1, 5 underscore 1, and 6 underscore 1. So in this case they also overlap. So to get the global stiffness matrix, you need to add the 2 in this part. So this is why it's highlighted. So here, so the global stiffness matrix, I'll show you how to arrange this. I think is easy. Don't worry about it. In the code I'll show you how to do this. So these ones have to be added for the two members because this overlap, so they have to be added together. The rest of this are obtained from the the member stiffness matrix. For example, the member 1 is numbered 1 to 6, so you can see this only has values from 1 to 6, so from 6 it is 0, so from 1 to 6. So this is, maybe I show you, so here this is the 6 by 6 matrix from member 1, so this is member, wow, it's difficult to write. Okay, let me just make it easy. So this is member 1, and this is member 2. So this overlapping area, you need to add. That's all. And to solve, you need to reduce the statistical indeterminacy. So for example, in the second node, these parts are called nodes. You can only break the members at the node. So member 1, AB is one node. So if you break it at that point, so that's node 2, the load, so that's two things. One, we assume this is the positive axis x, this is positive xy axis, and then also we assume that clockwise moments are negative. That means anti-clockwise moments are assumed positive, and so this is the reason for this. So this is why this moment is indicated here as negative. You can see there. The node 2, the force is indicated as negative 15. So that's one thing. Also, this is a hinge. We need to know that at a hinge, then the summation of moments is 0. So we know this from this is why I state that you need basic understanding of mechanics of structures. So we know that when there's a hinge, the summation of moment is 0. So we put that there. And also at the second node, there is no support there, so the shear force has to be 0. So still, so we know one. No, that's not right. Okay, that's still right, but maybe the wrong explanation. So for the N3, the horizontal force, so this is actually not a hinge, this is a roller support. Roller support means the force in the x direction is 0 and the moment is also 0. Simply put, at a roller support, horizontal force is 0 and moment is 0. So the reason why this is shown as 0 and the moment is also 0. And so this node 3. So node 2, we have the the axial force negative 50, and then the shear force is also 0 because there's no support there, and the moment is shown negative 80. So having known all this, you can isolate the matrix that represents N2, V2, M2, N3, and M3. Remember that you only isolate matrices whose external reactions are known, like this. So here, so isolate that. I'll show you how to do that in the program there and also there. So the ones that you do not know, I'll show you how to deal with them later. But still something interesting also, at node A, these are the displacements, but we know the properties of a fixed end is that this is 0, the movement in the x direction is 0, movement in y direction is 0, movement in the rotation is also 0, from basic understanding of mechanics of structures. And also for the roller even though it's a roller support, the forces in the x direction is 0, but still it can resist forces in vertical direction. So therefore the movement in the vertical direction is 0. And of course these are the fixed end moments as has been calculated previously. And so once you isolate, like I explained before, so 4, 5, 6, you isolate the ones whose external reactions are known as shown here, and these are the formulas that you follow. So you can see here this is represented by that. So let me use the same color to make it easy to follow. So so this is that, this is index L, and this is the isolated matrix, and this is my matrix. Please note the 10 power 3 outside. So they're basically the same matrix, except this one I factored 10 power 3 out, and this is the same there. Wait. So this fixed end matrix, and that's a fixed end matrix. So to help me solve, I combine this. If these ones cross the equation, the positive, there should be an equal sign here. If these ones cross this side of the equation, they become negative. So this is actually this column here is already the reactions. Okay, this is the P. This is the P matrix. So just not to confuse anyone, so this is the P matrix and this is the K matrix. So this is how Excel helps. So once these ones cross the equation, so assume they are not there, these ones cross the side of the equation and then results into that. So assume they're not there, so this and that, we're done with them. So we only have P matrix, K matrix, and the U matrix. So what you do is very simple. Multiply this by K naught, and also multiply this. Then I just write inside here by K naught. As you can see here, of course, by K minus 1. Of course, if you multiply K by K minus 1, you get an identity matrix, as you can see. So this is actual proof that what we're doing is correct. And the answers you can check for yourself. I think is self-explanatory versus the expected answers. Sorry. So this is proof that actually the code is giving the correct answer. So except I use different notations for you, it doesn't matter, you can choose your own. The most important thing is you understand what you're doing. So I use my own notations, you can see there, and the displacements. They use a different notation, but it doesn't matter. The important is the answers are exactly the same. So this is the answers, expected answers, and this is my answers from the code. So of course, once you can draw the BMD, the deflected shape, the shear force diagram, etc. So because the answers are the same, basically the solutions for the BMD and the deflected shape and the shear force diagram should be the same. But interestingly, you can see N1 is 65. This is from my solution. You can see 65 there. 36, V1 is 36. You can see 36 there. There might be some small differences, I think, due to the rounding off in forces. So M1 is 24, you can see there. N2 is negative 50. You might not see it here, but if you add 65, negative 15, that gives you negative 50, right? So N2 is 50. V2, this is a small value, like we say, should be 0, so close to 0. M2 is negative 80, so negative 40.11, negative 39 should be negative 80, right? So these two should give you negative 80 and 46. So 46 is in the orientation of 76 degrees from the horizontal. So this is 76. The angle there is 76. So if you want to convert to the vertical, it should be close to 44. So if you want to convert to where this is 90 degrees, it should be 44. Should be correct here. So 46, so you can see 46 here, and you can see 46 there. Pretty accurate. This 46.7, this 46.72. Yeah, fair enough. I think within the same range. So thank you very much. I hope you enjoyed this presentation. I'm going to open the Excel code now, and I will touch immediately after this video. Thank you very much for watching. Goodbye, and I will see you for my next video. So guys, this is the Excel sheet.